Imagine trying to count every single ant on Earth or every shining star scattered across the cosmos. Impossible, right? Yet scientists routinely come up with numbers so huge they sound almost unreal, like 20 quadrillion ants or more stars than grains of sand on all the beaches combined. How can anyone count what can't even be seen all at once? The secret lies in clever shortcuts and mind-bending math that turn the uncountable into something we can actually estimate. Counting every ant on Earth might sound like a prank rather than a research project, but ecologists have a surprisingly systematic way to do it. They start by selecting hundreds of sample plots, tiny squares of land scattered across rainforests, grasslands, deserts, even cracks in city sidewalks. In each plot, researchers sift through soil, turn over leaves, and use bait traps to collect every ant they can find. These painstaking surveys reveal how many ants occupy a given area, often expressed as ants per square meter, but the planet isn't uniform, so scientists repeat the process in wildly different habitats: steamy tropical jungles, frozen tundra edges, dry savannas, and bustling urban parks. Each location paints part of a global picture, showing how ant density changes with climate, vegetation, and human activity. They also record the weight of all those ants, known as biomass, to check that their counts match ecological expectations. Once they've built this massive database, they use statistical models to fill in the gaps for regions they couldn't physically sample. By multiplying the average density for each ecosystem by the total area of that ecosystem on Earth, they arrive at a staggering estimate: around 20 quadrillion ants, carrying a combined weight greater than all the wild birds and mammals on the planet. It's a reminder that sometimes the path to mind-blowing numbers starts with a scientist hunched over a patch of dirt, patiently counting tiny legs and antennae. It's a reminder that sometimes the path to mind-blowing numbers starts with a scientist hunched over a patch of dirt, patiently counting tiny legs and antennae. Astronomers face a challenge even bigger than counting ants: estimating how many stars fill our galaxy and the universe beyond when no one can see them all at once. Their solution is surprisingly similar to the ant approach: sample and scale up. First, astronomers aim powerful telescopes at carefully chosen patches of sky. Each patch is only a tiny fraction of the heavens but is studied in incredible detail. They tally every visible star, from the bright giants to the faint, barely detectable red dwarfs. By knowing the size of the observed region and comparing it with the total size of the Milky Way, they can calculate an average star density. They repeat this in many directions to capture different galactic neighborhoods: spiral arms, dense star clusters, quieter outskirts. These snapshots reveal not only how many stars are visible but also how they vary in brightness, age, and mass. Then comes the scaling: multiply the average density by the full volume of the galaxy, and you get an estimate in the hundreds of billions. For the entire observable universe, astronomers go one step further. Deep sky surveys like the Hubble Ultra Deep Field peer at a minuscule slice of space and count the galaxies inside. If that single slice contains thousands of galaxies, simple math lets scientists project how many galaxies, and thus how many stars, fill the cosmos. This method leads to a mind-bending number, somewhere around 1022 to 1024 stars, a figure so vast that even light years can barely contain it. Sampling alone can't reveal every hidden star. Many are too faint, too small, or shrouded in dust to appear even in deep sky images. To fill the gaps, astronomers turn to the physics of mass and light. Every galaxy shines with a measurable brightness, and scientists know roughly how much light different types of stars produce for every unit of mass. By comparing a galaxy's total luminosity with those stellar benchmarks, they can estimate how many stars are needed to create that glow, even if the stars themselves remain invisible. Another trick is to calculate a galaxy's mass using the way it bends nearby starlight, or how its gravity influences the motion of stars and gas. If the Milky Way weighs about 1 trillion times the mass of our Sun, and an average star is similar in mass to our Sun, astronomers can divide to estimate the total star count. Of course, they adjust for the fact that many stars are lighter or heavier than the Sun, but the calculation still gives a reliable ballpark figure. These techniques reveal stars that telescopes can't see directly, from tiny red dwarfs barely flickering in the dark to entire clusters cloaked behind cosmic dust. By weighing the light and the mass, scientists can sketch the universe's true star population far beyond the limits of our eyes and lenses. Even with careful sampling and galaxy-wide measurements, vast uncertainties remain. That's where advanced statistical modeling steps in. For ants, Scientists apply methods like the species-area relationship and bootstrapping to estimate how many colonies might exist in unsampled habitats. They factor in climate data, vegetation cover, and even satellite imagery to predict where ant populations thrive, then feed those numbers into computer simulations to narrow the global estimate. They factor in climate data, vegetation cover, and even satellite imagery to predict where ant populations thrive, then feed those numbers into computer simulations to narrow the global estimate. In space, astronomers wrestle with the unseen star problem. Many stars are too faint or hidden behind clouds of interstellar dust. To correct for that, they rely on the initial mass function, a statistical curve that predicts how many stars of each size a galaxy should contain. They also use Bayesian models and Monte Carlo simulations, running millions of digital universes to see which ones best match the light and motion we can actually measure. These techniques don't spit out a single perfect number. Instead, they produce ranges and confidence levels, like between 100 and 400 billion stars in the Milky Way. It's less about pinning down an exact figure, and more about revealing the scale of what we can never fully count, transforming guesswork into a science of probabilities. It's less about pinning down an exact figure, and more about revealing the scale of what we can never fully count, transforming guesswork into a science of probabilities. After all the sampling, calculations, and statistical wizardry, the final figures are staggering. Ecologists estimate roughly 20 quadrillion ants roam the Earth, a number so large that even if you counted one ant every second, you'd need millions of years to finish. Astronomers face even more mind-stretching math. Our Milky Way alone likely holds 100 to 400 billion stars, and when you extend the method to the observable universe, the estimate explodes to around 1022 to 1024 stars. That's a million trillion. Astronomers face even more mind-stretching math. Our Milky Way alone likely holds 100 to 400 billion stars, and when you extend the method to the observable universe, the estimate explodes to around 1022 to 1024 stars. That's a million trillion. But these numbers come with wide uncertainty. A single undetected ant supercolony or a population of ultra-faint stars could shift the totals dramatically. Dust clouds can hide entire star nurseries. Remote rainforests might harbor ant densities no one has sampled. Scientists know their counts are best viewed as ranges, not final tallies. Still, the fact that we can even approach these colossal figures is remarkable. It shows how clever methods, sampling, scaling, measuring light and mass, let us peek into realms that at first seem completely beyond human reach. And it sets the stage for the bigger question: why does trying to count the uncountable matter at all? At first glance, estimating the number of ants or stars might sound like a quirky trivia quest, but the stakes are much bigger. For ecologists, knowing how many ants inhabit Earth helps track the health of entire ecosystems. Ants aerate soil, recycle nutrients, and even influence plant growth. A change in their global population could signal shifts in climate patterns or habitat loss long before those changes are obvious to us. Astronomers, meanwhile, aren't just tallying stars for bragging rights. Star counts reveal how galaxies form, how matter clumps together after the Big Bang, and how dark matter shapes the cosmos. The density and distribution of stars help refine models of the universe's expansion and even guide the search for planets that might harbor life. In both cases, these massive estimates remind us of science's real mission, turning mystery into measurable knowledge. Counting the uncountable teaches us that with creativity and rigorous methods, even the most overwhelming questions can yield meaningful answers, and that our universe is both more knowable and more awe-inspiring than it first appears. When you step back, the lesson is bigger than the numbers themselves. Whether scientists are kneeling in the dirt counting ants or aiming giant telescopes into the darkness, they're showing us how curiosity can break the limits of what seems possible. When you step back, the lesson is bigger than the numbers themselves. Whether scientists are kneeling in the dirt counting ants or aiming giant telescopes into the darkness, they're showing us how curiosity can break the limits of what seems possible. We may never know the exact tally of ants marching across the planet, or the precise number of stars blazing through the cosmos, but that's not the point. What matters is the method, the ability to take something unimaginably vast and bring it within reach through observation, sampling, and bold mathematical reasoning. Each estimate is a reminder that even in a universe overflowing with mystery, patient human effort can turn the impossible into a story we can understand. And maybe that's the real magic, learning to measure the unmeasurable, one clever step at a time. From ants beneath our feet, to stars at the edge of the cosmos, Scientists have shown that even the seemingly uncountable can be brought within reach. By sampling small slices, scaling up, and applying clever math, they reveal patterns that connect the tiniest insect colonies to the grand design of the universe. We may never know the exact numbers, but each estimate reminds us how curiosity and persistence turn impossibility into discovery, and how much wonder still waits beyond the limits of our senses. We may never know the exact numbers, but each estimate reminds us how curiosity and persistence turn impossibility into discovery, and how much wonder still waits beyond the limits of our senses.